Alright guys, this is the third attempt at trying to make this video. Twice previously the whole system has crashed on me, so let's have a third go. Alright, so what we're trying to do here is find maximum and minimum points on a curve. So minimum points like this one down here, maximum points like this one at the top here where it says number 3, okay, and we're a minimum point where it says number 1. And I also want to briefly talk about this number 2 here where we have points of inflection. So let's start with points of inflection. Okay, on a curve you can have regions like this one here where it's concave down. Okay, so this one here, concave down. And you can also have regions like this one down here which is concave up. Now where the concavity changes, like in this bottom diagram down here, this point here where I'm pointing to at the moment, this is then a point of inflection where the concavity changes. You can have points of inflection which have a gradient of 0 at them. So y equals x cubed would be a classic example of that. So this is concave down, changes to concave up. It's a point of inflection therefore, but the gradient is 0. We will have a look at how to find those. All points of inflection in the next video. Excuse me. But in this particular example, what we've got here is this function here, y equals 6x squared minus x cubed plus 15x minus 2. And it's this curve that you see here. Okay, and what we're trying to do is to find the exact location of the minimum point number 1 and the maximum point number 3. And here's the key idea, that at maximums, minimums, and points of inflection that are horizontal, the gradient is 0. So this is a key idea. So what we're going to do is we're going to derive, we're going to let that derivative equal 0, find out when it equals 0, and they will be the x values when we have points where the gradient is 0. Okay, and we can see from this screenshot here that should be -1 and +5 for x. Okay, but often we won't have a curve in front of us, so we can't just read it off. So let's go through the calculus work. So I'm deriving this. This will be 12x minus 3x squared plus 15. So that's this here. Okay, and we want to find out when the gradient is equal to 0. So let that first derivative equal 0. Okay, and I prefer to have the x squared term positive, so I'm going to move everything to the other side, or putting it another way, multiply each term of the equation by -1. Okay, so we get positive 3x squared minus 12x minus 15 equal to 0. Now notice this is a common factor of 3. 3, 12 and 15 all have a factor of 3, so I'm going to take that out the front. That's going to give x squared minus 4x minus 15 in the bracket. Take the 3 to the other side, divide by 3, still end up with 0 over here. And x squared minus 4x minus 5 factorizes to x minus 5 and x plus 1. Okay, finding it when they are equal to 0, when each of them is equal to 0 gives 5 and -1. So that's all great. Now what about this little table down here? What's this about? Well, what we want to do is we want to use the idea that at a minimum point the gradient changes around the minimum point in the following way. Leading up to a minimum point, the gradient is negative, so we've got a negative gradient there. At the minimum point the gradient is 0, so it's a flat line. And then after the minimum point, in that same region around it, but after the minimum point, the gradient becomes positive. Now at a maximum point, let me just change the pen color, the gradient leading up to a maximum point is positive. At the maximum point the gradient is 0, and after the maximum point in that same region, but after the maximum point the gradient changes to negative. So what we're going to do is we're going to use this first derivative, which can tell us the gradient. We're going to use that to put some points into this first derivative around the maximum and around the minimum in the following way. So let's take x equals 5. So in my little table here, 3 columns, 2 rows, put 5 in the middle. Now over here you can see I've put y dash, indicating this is the derivative, and at x equals 5 I've drawn a flat line. Okay, flat line there. Why? Because the gradient is 0 at x equals 5. Let's put a value such as 4, which is close to 5 but less, into our first derivative. So we go 12 times 4 is 48, 4 squared is 16, negative 3 times 16 is 48, so actually positive 48, take away 48 is 0, plus 15, now that's positive. So I'm drawing an upward sloping line there. Let's take something like 6 and put that into our first derivative. So that's going to be 72. 6 squared is 36. Negative 3 times 36. If you take the 72, take away that value and add 15, you end up with a negative value. Okay, so it's a downward sloping line then. Okay, so you can check what that exactly is using a calculator if you wish to, but it's definitely negative. So what we have then is we have a positive gradient leading up to 5. At 5 the gradient is 0. After 5 the gradient is negative. Therefore that's definitely a maximum type shape. If you do the same thing with x is negative 1, which is our other value here of interest, so we've dealt with x is 5, now we're dealing with x is equal to negative 1. Okay, at negative 1, same 3 columns, 2 rows, x, y dash here. At negative 1, the gradient is 0, so flat line. Take x is greater than negative 1, and that's pretty easy to work with. We'll use 0. So 0 into our first derivative gives 15, which is positive. Let's take negative 2. If you put negative 2 into our first derivative, what do we get? Negative 2 times 12 is negative 24. Negative 2 squared times 4, negative 2 squared is 4 times negative 3, that's going to be negative 12. So that's negative 36. If you add 15 to negative 36, well, it's definitely going to be negative. Okay, so we've got a negative slope there. And let me just rub out that because it looks messy. Okay, so what have we got? We now have indication then that this is negative gradient leading up to, oops, that is rather ginormous size. Did not expect that. Okay, let me just see if I can change that. Let's rub that out. So negative, great colour. What the heck is happening there? Okay, not cooperating. Just a moment. Okay, there we go. So negative gradient leading up to negative 1. At negative 1, gradient 0. After negative 1, gradient positive. So going like this, that definitely is a minimum shape. So we know that when x is 5 we have a maximum, when x is negative 1 we have a minimum. The only thing left you have to do is to get the y value. So when x is 5, what is the y value here? And when x is equal to negative 1, what is the y value in about that position there? I'm going to let you find those. So substitute 5 and negative 1 into the original function, and I'll ask you tomorrow what the exact coordinates are. Okay, so hopefully this doesn't crash on me anymore right now, and I'll try and save this and get this up